My name is Luke Tillmann. I'm an eco-hydrologist with Seebeck Eco Engineering out of Minneapolis, Minnesota, and I'm talking today about EcoFIP, which is the Ecological Floodplain Inundation Potential tool that we use to assess multi-objective floodplain restoration opportunities. I want to start the presentation with a bit of background about the problem that we're trying to solve before getting into the EcoFIP tool itself and how it works in kind of a broad overview, and then end on some applications of the tool that we've used, largely in the state of California. And so land use changes and engineering practices within North American watersheds have had an array of impacts on ecosystem health. We've contributed substantial nutrient pollution to areas like the Gulf of Mexico, which has had substantial impacts on offshore fisheries. We've dramatically reduced floodplain habitat and surface water-groundwater interactions, and paradoxically increased flood risk for millions of people as a result of extensive leveeing and other ways of removing active river channels from their historical floodplains. And while we have a good understanding of what the bad actors are within a given system, there historically hasn't been a great way to get to effective floodplain restoration projects at scale. So starting with a watershed scale prioritization scheme and getting all the way down to site selection, using cost versus uplifts to be able to do iterative design concepts, and ultimately in a way that fosters alignment between project partners, agencies, and funding organizations. And we aim to address all of those kind of shortcomings with the EcoFIP tool. And we think about EcoFIP as this kind of funnel that we use to get from the large scale, kind of the river system or landscape scale, all the way down to site level analysis and conceptual designs. And we do this through a series of analysis tiers. Tier 1 is the large scale inundation potential, and that is really looking at where can we get water out onto the floodplain if we were to do things like levee setbacks or floodplain grading, side channel reconnections, or other physical modifications, as well as changes to the hydrology of a system. So really asking where can we first get water out onto the floodplain. In Tier 2, we refine that a bit by saying not only where can we get water out on the floodplain, but how suitable is that floodplain inundation for an array of purposes that we care about in a given system? This is our multi-objective site identification and prioritization, where we're actually dividing the landscape up into spatial units, which might be parcels or some kind of grid cell or river miles. And we're asking within each of those, how is inundation driving floodplain rearing habitat for Chinook salmon, for instance, or how much recharge are we going to be getting in an average water year? We're starting to use different criteria and metrics to be able to describe how these sites fare against each other. And once we identify high priority restoration sites that look like they have a lot of potential for uplift, we then go into Tier 3, which is our conceptual design, where we use the same tools within EcoFIP as we had in Tier 2 to quantify the benefits of actually making these physical landscape modifications or flow changes. And so starting with Tier 1, what we really start out with is a digital elevation model, oftentimes derived from a LiDAR data set, and a hydraulic model. And hydraulic models are used to simulate flows and understand how high water surface elevations get as a result of those flows, how fast water moves, and how water interacts with structures and other physical pieces of the landscape. And so these are things like HEC-RAS is a common hydraulic model that we'll use. And what we do is we start out by taking the hydraulic model, running it for a range of flows that cover kind of the expected hydrology that we're looking at. And we first extrapolate these water surface elevations for each of those flows. We take the water surface elevation that the model gives us, and we project those over the floodplain through levees or other type of topographic barriers to get a gridded data set of water surface elevation for each flow that we model. From that, and in conjunction with the digital elevation model that we have, we can produce our height above river maps. So this is showing at a given flow, which in this case is 30,000 CFS on the Wabash River along the Indiana-Illinois border, how high is the land above the water surface elevation at this particular flow. And so areas in blue are showing those that are below the 30,000 CFS water level. These are areas that could be inundated at 30,000 CFS if you were to make connections like levee setbacks. Areas in green are 0 to 5 feet above the water surface elevation, and areas in brown and black are getting 5 to 10 or more feet above the water surface elevation. And if you look closely in this picture, you can actually see thin black lines kind of following along the main channel, and these are actually the levees within the system showing up in the height above river map. From height above river, we can also get to depth, which is an important input for us to understand rearing habitat quality for Chinook salmon or for steelhead trout or others. And depth is essentially the inverse of height above river. We're where we had a negative height above river in that prior map. That's a positive depth value that we have. And then from depth, the tool is also determining the connectivity. And remember that we had started by projecting water surface elevation through levees and looking beyond levees or other types of topographic barriers. And so this is where it actually comes back and says, at a particular flow, what are the areas that are physically connected to the river corridor? Those are being shown in blue. And the areas that are in red are the ones that could be inundated. Those are areas that are below the water surface elevation, but because of levees or other types of barriers, they're not currently connected. So that's another kind of primary output from this Tier 1 analysis. And this is an important map that kind of summarizes across a range of flows that we're looking at. So we're going from 1,000 CFS up to 300,000 CFS. And this is using those same data sets to kind of show what is the potential activation footprint at each flow. So each pixel on this map is kind of saying that this is the minimum flow that you need to be able to activate a given area of floodplain if you were to be able to make a connection over to it. So this is kind of the potentially activated area. And so all of that is EcoFIP Tier 1. It's really asking that question of where can we get water out on the floodplain. Once we step into EcoFIP Tier 2, we're trying to ask the question of how suitable is that inundation to drive various processes. And one that we're really interested in a lot of these rivers in California is what is the ability of this to drive off-channel habitat, where we look at the depth of inundation. Sometimes we also look at the velocity of that inundation, and we also look at the seasonality of the flow to understand when is it actually providing meaningful rearing habitat. And the way that we're actually extrapolating this data into these spatial analysis units that we talked about previously are that we build these rating curves that describe how each site functions relative to flow. So we can see in the bottom curve, the blue line is showing the amount of inundated area and how it increases as a function of flow. The more flow we have, the more inundated area that we have from that animation. The green line is actually showing the weighted usable area. So this is the amount of habitat area, the amount of rearing habitat within this system. And we actually see that we increase up to a point with increasing inundation. But by the time we get more than 5,000 or 6,000 CFS, we actually start having lower and lower habitat availability as a result of that water getting too deep and in some cases too fast moving to provide reasonable habitat. So once we extract these rating curves, we can then apply a daily flow time series to build out heat maps, essentially, of where the hotspots for annual juvenile Chinook rearing habitat are, for instance. And so on the second gridded picture from the right, that is showing annual juvenile Chinook rearing habitat. The areas in red are kind of the lowest available habitat, and the areas in green and blue are progressively higher habitat availability. So this is looking at if you were to make these types of connections, what would actually provide the most habitat. We can see some features like oxbows showing up in this as being potentially high quality habitat. And as I mentioned, this is a multi-objective tool. We're often thinking about other types of floodplain management actions. And so on the right-hand side, you're seeing annual groundwater recharge and kind of a corresponding heat map for what areas should be prioritized if that is kind of one of your main interests within that portion of the Sacramento River. So once we go through that step in Tier 2 to kind of rank these different sites against each other, then we step into Tier 3, which is our conceptual design, where we take those high priority restoration areas, we develop a library of rehabilitation actions that might include levee setbacks, floodplain grading areas, side channel creation or alcove creation. We use those to develop and evaluate an initial set of concepts that we refine through several rounds of stakeholder engagement, and we produce project costs and benefit comparisons that I'll touch on briefly, and ultimately select some high quality sites to take to higher levels of design. And so that's our overview of the EcoFIP tool itself. And now I just wanted to show a few different applications of us, largely in the state of California, applying different portions of the EcoFIP tier matrix that we looked at. And one of the ones that we're currently working on right now is this basin-wide planning study for tributaries of the San Joaquin River in the southern Central Valley of California for the California Department of Water Resources. So we're looking at hundreds of miles of river between the upper San Joaquin, the Merced, the Tuolumne, Stanislaus, and Calaveras rivers, and really trying to quantify the amount of off-channel habitat, rearing habitat that exists under existing conditions, and trying to think how that's going to change in the future when we're looking at climate change. This is a snowmelt dominated system for most of these tributaries, and that's going to, the hydrology is going to be shifting dramatically as a result of climate change. And it's also going to be changing in the face of reservoir reoperations to handle those different flows from climate change, as well as different different ways that the system is being operated. And the question is being asked, how much available habitat is there currently, and how is that going to change under these range of possible scenarios that we'll have, managing the system differently, and what types of actions might we need to make to actually make up for those changes that we're seeing. At a higher level of detail, and zooming in on the upper San Joaquin River, we've also used this to create restoration concepts in a highly degraded landscape. And so for Site 16 on the San Joaquin River, looking on the left-hand side, this is 1937 imagery where you can see some intact upland and riparian zones, as well as kind of a healthy river corridor. And fast forward to 2022, gravel mining has essentially stripped away a lot of that ecological function. It's created large pits in the river that the river has recaptured. We've removed a lot of that riparian corridor and generally left this in a highly degraded state. And so we've had concepts to try to figure out how to fix this, using EcoFIP to not only identify the sites that could have this type of uplift, but also using EcoFIP to create these concept digital elevation models and understand the cost versus benefits of doing these projects. And so for one example, we've proposed recontouring some of the floodplain area here, cutting down areas of high ground, creating a side channel, using some of that cut to actually fill in some of these ponded areas, and then exclude some of these larger gravel pits so that fish can't get into them under high flows, but they can still be used to trap high flow events for kind of transitory storage and flood reduction. So we use EcoFIP not only to produce the concept digital elevation model, but also to look at the inundation characteristics of existing ground versus the future ground that we can also use to understand in a grading analysis. Where are we doing our cut and fill? How much cut and fill are we doing? And how much grading area are we doing? How much vegetation are we disturbing? And ultimately, considering all of those costs, how much benefit are we actually getting as a result of doing that particular project, and deciding whether those benefits outweigh the physical landscape modification costs that we have. We also have applied this type of approach in the central coast of California, again for the California Department of Water Resources, but also in conjunction with the U.S. Army Corps of Engineers, to look at where levees could be set back and floodplains could be lowered, initially for a flood risk reduction study, but ultimately trying to find ways that those flood risk reductions could be done in a way that maximize rearing steelhead habitat, as well as managed groundwater recharge, essentially. We've also, within that analysis, looked at where the Corps can prioritize borrowing material to build levees. So they need to be able to dig down portions of the floodplain to mix with some material that they're bringing in from off-site to construct these levees. And we've actually gone through several design iterations to figure out where they could be pulling that material and how they could actually be grading that material out in a way that not only provides the material that they need for levee construction, but also in a way that we're lowering the floodplain and creating off-channel habitat for steelhead trout in an otherwise pretty incised system. We've also, in the same system, looked at climate resiliency to ask the question of, under various future scenarios of a range of precipitation projections and temperature projections, how much more or less habitat are we going to be seeing under existing conditions, and how might we actually mitigate for that based on designs that we might do? How much material might we need to remove, or how much lowering might we need to do to actually make up for the effect of climate, potentially reducing flows, seasonal inundation, and off-channel habitat in these areas? And finally, zooming up to the Sacramento River in Northern California, we've applied EcoFIP to look at fish stranding hazard assessments. So this map on the left is showing a few different images going from blue at 10,000 CFS up to this pink color ramp being 80,000 CFS. These are the flows at which each portion of the site becomes connected to the river. And we're trying to look at if there's a pulse flow that comes through this area and you get up to 80,000 CFS or more that activates these floodplain areas, what are going to be the areas that become disconnected and potential stranding hazards on the descending limb of this hydrograph? And how do we prioritize which of those stranding hazards to try to reconnect to the river to ensure volitional passage of these outmigrating salmonids? And so that was a real quick kind of overview of all the different ways that EcoFIP can be used, but ultimately it's an intermediary between high-level decision support tools that get you to priority watersheds, for instance, and detailed engineering design. We've applied it extensively throughout California, especially for Chinook and steelhead rearing habitat studies. It efficiently conducts watershed scale feasibility studies and rapid conceptual design iterations. It can be tailored to use a large array of multi-objective floodplain metrics. We've talked a lot about fish and recharge, but there are many others that we can look at. Promotes alignment between project partners, stakeholders, agencies, and funding organizations, and ultimately increases the rate at which effective multi-benefit floodplain restoration projects can be designed and implemented. I'd also like to thank our clients and partners over the last 5 years of developing this tool, as well as my co-authors on this, and our contact information is shown at the bottom of the screen. Thank you very much.